Ever looked at a smart gadget and thought, man, I really wish I could build that myself? Well, welcome to this explainer. Today, we're diving into a seriously phenomenal resource for aspiring makers, tinkerers, and engineers. We're going to unpack the wild world of microcontrollers and coding and see exactly how to bring the physical and digital worlds together in a way that's surprisingly accessible, totally regardless of your prior experience. It's a super common dream, right? We see all this incredible tech around us and think, I'd love to build something like that. But, we usually stop ourselves, basically assuming the barrier to entry is just way too high. Well, this explainer is going to show you exactly how accessible that dream actually is. We're breaking down Ryan Turner's foundational book, which totally proves you don't need some multi-million-dollar lab to create real, functioning smart devices. To do this, we're exploring the core concepts laid out in Arduino Programming 2 Books in 1 by Ryan Turner. Now, exactly like the title suggests, this is a comprehensive guide. It's designed to take you from absolute beginner concepts, like just figuring out what a circuit board even does, straight through to this incredible leap into intermediate-level tinkering. We're talking getting to the point where you're suddenly working with actual GPS modules and full-blown sound synthesizers. It's pretty wild. So here's our blueprint for today. We're going to mimic the two-part structure of the source material. We'll quickly cover what Arduino is, why it's got such big advantages, dive into the hardware, how to code it, and finally, we'll step up your game with those intermediate modules. All right, let's jump right into section 1. What exactly is Arduino? We're going to demystify this microcontroller right now. So, the absolutely crucial point here is that Arduino isn't just a piece of metal and silicon. It's a whole open-source ecosystem. It's basically a perfect marriage between a programmable physical circuit board, the hardware, and a software coding environment, which is known as an IDE. Think of that IDE like a digital canvas for your code that runs right there on your computer. You honestly can't separate the two. They're literally designed to work perfectly together. And this brilliantly illustrates the really simple 4-step workflow that magically turns a piece of code on your laptop into a real-world physical action. First up, you get the hardware. Second, you write the instructions on a standard Windows, Mac, or Linux computer. Third, you upload those instructions to the board using a simple cable. Yep, just a good old-fashioned physical cable. And fourth, the microcontroller stores that code and runs it. So, just as an example, your code could tell a light sensor to trigger a loud alarm sound whenever a door opens. Pretty neat, right? Moving on to section 2. What's really interesting here is why Arduino has become such a massive global phenomenon. Let's look at the 6 big advantages. These 6 advantages really explain the platform's explosive popularity. First off, cost efficiency is massive. A pre-assembled board often costs less than $50, which is just a tiny fraction of what older microcontroller platforms used to cost. Combine that with a cross-platform IDE that works perfectly whether you're an Apple user or a diehard Linux fan, plus completely open-source software and hardware with 0 licensing fees. And honestly, that completely open-source ecosystem means you aren't just buying a board. You're gaining access to this massive global community. You're literally standing on the shoulders of giants here. If you hit a roadblock, chances are someone on the internet has already solved it and written a free C++ library for it. So yeah, it's affordable, incredibly straightforward, and heavily supported. Let's move to section 3 and see how this hardware is actually put together. What are we physically holding in our hands? If you look closely at an Arduino board, you'll spot this prominent black chip. That right there is the ATmega microcontroller. This is the literal brain of the entire board. It's the exact component that receives the instructions you wrote on your computer and actually executes them. Honestly, without this central ATmega chip, all the other pins and connectors on the board would have absolutely no functionality at all. But not all brains are the exact same. The Arduino family is surprisingly vast. The book covers everything from the super beginner-friendly Uno, which runs at 16 megahertz with 32 kilobytes of memory, all the way to much more advanced boards. Need more speed and a built-in code debugger? The 32-bit Zero ramps things up to 48 megahertz. Or maybe you're building something that needs to talk directly to an Android phone. The Mega 80K is specifically built for that. Choosing the right board really just boils down to your project's specific power and memory requirements. And this brings us to a really vital conceptual distinction to ensure your success. The physical pins on the edge of the board are what sense the outside world, like, reading a temperature or sensing darkness. But it's the software logic inside the brain that tells those pins what to do with that information. So, think of it this way. The hardware provides the senses and the muscles, but the software, that provides the intelligence. Speaking of software logic, let's dive into section 4. Let's look at how we actually write these programs, which, by the way, the Arduino community affectionately calls sketches. Because the Arduino coding language is fundamentally based on C++, it is incredibly precise. Strict syntax rules are basically non-negotiable. As Turner points out, every single program statement absolutely must end with a semicolon, and your blocks of code need to be enclosed in curly braces. I'm not kidding. If you miss a single semicolon, the board simply won't understand your commands, and you'll probably spend 20 minutes tearing your hair out looking for it. It's kind of like trying to read a long paragraph with zero punctuation. Once you've got the syntax down, you'll start using functions. These two fundamental functions basically act as the eyes and hands of your program. Digital read allows you to read a specific pin, say checking if a user just pressed a physical button. Digital write is its counterpart. It sends an output signal, perhaps telling an LED light to turn on. It's simple but powerful. Now, to connect the input to the output, we use control structures. This right here is how you give your project actual intelligence. By using conditionals like the if statement you see here, your program can make real decisions. In this example, the code inside the curly braces will only trigger if the button is actively being pressed. It's a simple logical comparison, sure, but stringing these together is exactly what allows you to build incredibly complex behaviors, like a robot deciding to suddenly turn left just because its sensors detected a wall. All right, now we're transitioning into Section 5, the second half of our explainer, which mirrors the second book in Turner's Guide. We're moving past the basics to unlock some truly exciting intermediate techniques and modules. I really love this quote from the text because it perfectly captures exactly why you'd want to push past that beginner stage and learn the intermediate modules we're about to discuss. It says, "This is why Arduino is a tinkerer's dream. You can do a whole lot for a very low price. You genuinely can achieve professional-level hardware automation right from your living room desk for literally pennies on the dollar." The sheer variety of modules you can integrate once you master those basics is honestly staggering. By adding these advanced modules, you vastly expand your board's horizons. It's literally like giving your project superpowers. You can hook up a GPS receiver to track exact location data. You can use servo motors and stepper motors to introduce physical movement, to build a fully autonomous robot. You can connect to the internet via wired Ethernet or Bluetooth, or even digitize and synthesize your own sounds. The board basically becomes a central hub for almost any sensor you can possibly imagine. And this brilliantly illustrates the ultimate goal of Arduino programming, seamlessly linking the physical world of sensors to the virtual world of processing. The book gives a really great example of this. Imagine building a smart jacket equipped with piezoelectric sensors. Visual LED feedback wouldn't really help the person wearing the jacket, right? But by programming the Arduino to send vibration feedback through the fabric based on how they move, you've completely bridged the physical and virtual realms. That's a real game changer. So a simple $50 board, some basic C++ syntax, and a few snap-on modules can empower you to build everything from a basic smart nightlight to a vibrating interactive jacket. But the real takeaway here isn't just about the wiring and the code. It's about a fundamental shift in your mindset. You're no longer just a consumer of technology. You now have the exact blueprint to become a creator of it. So look around your room right now. What in your life is just waiting to be automated, upgraded, or totally invented? What will your first project be?